Hello, students. This is Dr. DA again, and today I am going to walk us through this particular lab, which is called the Qualitative Analysis of Selected Group 2 Cations. And my intention is to take you through some of the reactions. I recommend that you have the lab manual with you and that you follow along briefly. You will not be doing these procedures, but it'd be good for you to know more or less what you are doing. And of course, at some point, what we will do is we will refer to this flow chart because we'll walk through each of the steps and what are the expected results. All right, so let's do this. Let's go to our makeshift whiteboard here and let's talk about group 2 cations. Let me set this up here first of all. Okay, I want to make sure this is properly focused. So these are the group 2 cations, and the four that we're going to be studying are copper 2, cadmium, bismuth, and tin 4. Don't forget that copper and tin are metals that form other kinds of ions, but we're only going to study these two. What characterizes group 2 cations is the formation of insoluble sulfides at a low pH. That's what allows them to be separated, okay? Okay, let me see if I can, see, this guy is not working very well here. Hold on a second, for a moment. I'm sorry, I may have lost you there for a little while. So here we go. This is the page I was referring to. So the group 2 cations, copper 2, cadmium, bismuth, and tin 4. And what characterizes them is the formation of insoluble sulfides at a low pH. So let's consider the following. We need to generate sulfides in solution. So we need a source of the sulfide ion. But most sulfide compounds are actually insoluble anyway. So we could consider the following. Consider hydrogen sulfide, which is a gas. And when you bubble it into water, it forms this aqueous hydrogen sulfide. But as you can imagine, it is an acid. And so it would essentially be in equilibrium ultimately with 2 protons and the sulfide ion. So in other words, what we need to do is figure out a way of bringing hydrogen sulfide into a solution that has these ions so that we can generate the sulfide ions to precipitate them. Here's the problem. Hydrogen sulfide gas is pretty toxic. If you carry out this experiment in the lab, you will realize you'll have to work in the fume hood. Otherwise, the fumes can be very annoying. It's a very foul-smelling substance. So what we do is, instead of using hydrogen sulfide directly, we use a different compound to generate the sulfide ions. We use a compound called thioacetamide. And I have a formula here on the bottom. So this is thioacetamide, which we abbreviate TAA. And as you can see, thioacetamide in water decomposes into an acetate ion, ammonium ions, and hydrogen sulfide. And therefore, this is what becomes the source of our ions for our experiment, okay? So this is going to provide our ions of sulfide for our experiment. So what we will do therefore is we will have our mixture of ions, known or unknown. So you have a mixture of the cations, all right? We will react it with TAA and water. And in order to get our precipitates, our sulfide products, right? It turns out that this reaction is endothermic. So what we're going to do is we're going to carry this reaction with heat so that, as we learned in the Le Chatelier principle, we can push the equilibrium of this reaction towards the right. Okay? So that's how it's going to work. Now, because hydrogen sulfide in solution is acidic and it has an equilibrium, its ionization here is going to depend on essentially the pH of the solution. So let's consider what would be the Ka for that equilibrium. So Ka, right, would be the hydrogen concentration squared times the sulfide concentration divided by the concentration of the unionized hydrogen sulfide in solution, which we would call sometimes hydrosulfuric acid. Notice that if I rearrange this expression, I get the following. The concentration of sulfide ions would be equal to the Ka times the hydrosulfuric acid concentration divided by the hydrogen ion concentration. So again, let's consider two scenarios. Let's say that we are at a high pH, right? Which means a low concentration of hydrogen ions. Well, what that is going to cause is, since the bottom part of this is low, it means that now your sulfide concentration is high. And what's going to happen in that case is that pretty much most cations will form a sulfide precipitate. And that includes the other groups, the group 3 cations that we don't want to co-precipitate with ours. At a low pH, what happens is you have a higher concentration of hydrogen ions, which means that now our concentration of sulfides is low. If the concentration of sulfides is low, then there's no precipitate at all, right? There's not enough sulfides to drive our cations into a sulfide precipitate. So what we try to do is find some kind of a range. And what we do is we're going to aim for a pH somewhere around 1 or a little less, all right? And what will happen is at that pH, we have enough sulfide ions to precipitate our group 2 cations, but not so much that other cations will precipitate, all right? So that's the process. So if you go through your, what am I talking about here? Sorry. If you go through your procedures here, right, you will see that you are going to be starting this experiment with a mixture that contains all of our ions here. And you're going to carry them through these different steps. The first step is you're going to be making sure the solution has a sufficiently acid pH. And once more, we have for you the following. We're going to have a document you're going to be able to download Sorry, let's see. Oh, here it is. Sorry. That has the results at each step of the way. So like it shows here, you're going to be starting with this, right, on this mixture of knowns. In other words, this mixture has all four of the ions in it, all right? And the first thing you'll do is you will adjust the pH, like it shows you here, to a, somewhere around like between zero point 0.5 to zero point 0.8. You can see that here in this picture, all right? So make sure you have this document with you. It should have been included in the assignment box. That's the first step we do. So at this pH, we can be confident that when we add the thioacetamide, we're going to be generating just enough sulfide ions to precipitate our group here. And what you're going to end up is after centrifugation, you're going to have, oops, I'm sorry, you can probably not see that very well. Oops. Okay, let me get that out of the way here. Okay, I'm having a hard time kind of like zooming in. Oh, here we go. Zoom into this, you can see the flow chart a little better. All right. So basically, you're going to have your ions all precipitated in the forms of sulfides. So this is the first step in the process. And our next step is going to be to start separating the ions and then confirming them. Okay. So let's see what happens next. Our next step in the procedure consists of adding KOH, potassium hydroxide. Let's see how that is going to help us, all right? So let me come back here to our screen, all right? There we go. And what we're gonna do first is we are going to add KOH to our precipitate. So we have essentially, right now at this point, we have our mixture that has, the copper 2 sulfide, the cadmium 2 sulfide, the bismuth sulfide, and the tin sulfide. All of these are solids, and they have different colors. And what you will see is essentially a very dark mix, because in general, the bismuth sulfide precipitate is very dark, and it kind of like dominates the color of your precipitate, all right? Now, our first step here is to add KOH. So what does that do for us? This is to separate and confirm the presence of tin. Remember that we always have a strategy where we first separate one ion at a time, and then we confirm its presence. Well, it turns out that if you have this sulfide of tin here, in the presence of sufficient hydroxide ions, it forms a complex between the tin ion and the hydroxide ions. This is what is called a complex ion. Let me see, sorry, this is minus here. All right. And if we finish balancing the equation, there is another product here that we don't care much about. It's going to be a soluble form of the tin sulfide here. But what's significant is that in essence, what happens is that at this point, if you add KOH, you've essentially dissolved the tin sulfide. And so if you now respin this mixture, you are going to have a residue that still has the copper sulfide, the cadmium sulfide, and the bismuth sulfide in your precipitate. but you're now gonna have this tin that is complexed with the hydroxide ion, and it is soluble. So this will be in the supernatant. All right. So essentially what we've done is we've dissolved the tin 4 ions out of that pellet. And now in order to confirm, what we need to do is we need to reverse this process, remove the hydroxide ions, and we do that by neutralizing them. So if we come here and we add acid, and then a little extra TAA, what we'll do is we will reprecipitate that original tin sulfide, tin 4 sulfide that we had in there. And what is significant about this is that it should have a particular color. So let's go back to our document here that you've been given. All right, let me show you what it looks like. So here we are. And as we remember, what we did was we adjusted the pH of our mixture, right? We generated, as you can see, this dark precipitate here, right? And then after the KOH and reprecipitation, we obtained, oops, sorry. Let me use something else here to move around. There you go. Okay, let me move around. There we go. We have a kind of like a blurred, kind of murky, kind of like supernatant. And after we add acid and we add thioacetamide again, we end up with this precipitate, which has a brown color. That is our tin sulfide, tin 4 sulfide, and this is the confirmation that we have of the presence of that ion. All right, let's come back here. And this is going to be, like I said, kind of like a brown color precipitate. Okay, now we have these guys here, and we need to continue separating these guys, all right? So let's go and see what we're gonna do with those. Let's see how we are going to now identify the presence of cadmium. Identify cadmium. Remember, or actually, as we've mentioned before, but as we'll study in other chapters, the cadmium sulfide is always going to be in a small equilibrium with the actually dissolved ionic forms here, right? These are the ions. Now remember that the sulfide ion is always going to be in equilibrium with its acidic form, the sulfuric acid. So let's say that I were to add acid to this precipitate. Well, what would happen is that now the sulfide ions would react with the excess of hydrogen ions to give me back the dissolved hydrogen sulfide. But here's the thing. If the acid that we add happens to be HCl, it turns out that in the presence of a decent amount of chloride ions, the cadmium ion itself forms a complex with chloride ions. And we will study these complex ion chemistry later in the semester. But think about it. If we add HCl, what we are doing is we are pulling away sulfide ions via this equilibrium here. So Le Chatelier pushes this equilibrium to the right because we're increasing hydrogen ion concentration. And since at the same time we're increasing the chloride ion concentration, we are pushing this equilibrium to the right, which means that in essence, what we are doing is the net effect, we are going to be dissolving the cadmium sulfide precipitate. That's the net effect. And so our process now consists of, okay, how do I confirm? Well, you confirm by bringing the solution back to a basic pH. And in a basic pH, we essentially are removing the this equilibrium here, right? And we add TAA. And in a basic pH, the thioacetamide, produces a lot of sulfide ions, which basically brings this back up the ladder here, and essentially you re-precipitate the cadmium sulfide ion. Let's see what that looks like in our document. All right, so we were here. Oops, sorry, that's not the one. I apologize for that. Okay, hold on. Still, you can tell I'm still a little rusty at these things. Okay, here we go. So here we are. Remember, in our process, we were over here, right? We had our precipitate with the 3 cations in the form of sulfides. We added HCl, so we redissolved the cadmium, and now we reprecipitated. And what's important here to note is that that particular precipitate has a kind of like a bright yellow color, all right? So as soon as you added the ammonia to make it basic and the thioacetamide to add more sulfide ions, now you have a pure precipitate of cadmium sulfide, and it has a yellow color. All right, so we've got that one. Let's come back here. And what we're saying is that in this case, one second. Let me get us back to our mode here. So remember that the idea here is that this is going to be a yellow precipitate, okay? Now we have to separate and identify the other 2 ions. These are the copper and the bismuth, all right? So let's go to that. And let's see how we're going to identify copper 2 and the bismuth ion. So remember, at this point, we have both in a pellet. This is, the stage where they are right now. They are in the form of a copper 2 sulfide and a bismuth sulfide. So what we're going to try to do now is to separate them, all right? So it turns out that in the presence of nitric acid, if it's very hot, what we can do is we can redissolve these ions. And by a different reaction, it turns out that the sulfide itself becomes converted into sulfur. So this is like a little side reaction here. what's going to happen is that in the presence of our hot nitric acid, our sulfide is going to be converted into elemental sulfur, which will be solid and sometimes looks like a little kind of like a light yellow precipitate. All right, like a light yellow precipitate. But what this did was what it solubilized these guys. So what I'm going to do now is I am going to add ammonia. So after I separate that pellet out and I have a supernatant that has the ions in question, I'm going to add ammonia. Ammonia is going to separate these two for the following reasons. In the presence of ammonia, copper ions also form a complex ion with ammonia. This complex has the following form, and we can abbreviate it this way. This is going to be a purely soluble complex, and it has a deep blue color. However, the ammonia, because it is basic, it produces hydroxide ions in solution. And in that case, what will happen is that these hydroxide ions that come from the basic properties of ammonia will actually push the bismuth ions that were in solution into an insoluble bismuth hydroxide, which should be of a white color. So in one step, by the addition of ammonia, we separate and at the same time confirm the presence of both of these cations. The copper 2 as a deep blue supernatant and the bismuth as a white precipitate. So let's go and check our document again, and let's see where we're at. Here we were, just a moment. So after we took those, the pellet that had the bismuth and the copper ions, remember that over here, we had added the hot nitric acid. All right, here we go. It was, I'm having a hard time getting this guy to work here. Okay, here we go. Okay, I can't get it to work. Sorry about that. I apologize for that. The nitric acid will dissolve our bismuth and our copper ions. You can see them there. I'm going to try this again, see if I can get this pen to work. Okay, here we are. Wow, I can't seem to be able to get this guy to work. Okay, I can get it to work. I'm sorry about that. I apologize. The ammonia is now going to generate a deep blue supernatant and a white precipitate. And that will be down here at the bottom of your document. There's the white precipitate of bismuth, and there's the deep blue color complex of the copper. If you want to visualize them, of course, you'll spin them and you'll see the difference. At this point, there's no need for further decanting or separation because you can see them both in there. All right. So this is the way that we separate these ions. Now, let me come back here. It's very important, therefore, that you go back and when you went to the assignment, you're going to be watching this video of my explanations, right? You are also going to be downloading this document that has all of the steps and what you observe at each step throughout the process. And then, as we did in the previous lab, you're going to have a file uploaded into your particular, into your grade book that will have a set of pictures like this one. And what you'll have to do is look at the pictures in there step by step. And according to whether they match or don't match the results at each step, you're going to be able to decide which ions you have. So basically, in your original document here, right, with your procedures, let me show you that. What you'll do is you have a data sheet here on page 58. I'm sorry, data sheet number 1 is on page 59. And essentially, by observing that document that is right now on the assignment box in your Canvas, you can write down observations of these different things, you know, kind of like just as if you had been the one doing the experiment, right? So you'll write down your observations and notes there, and so forth. And then the next data sheet number 2, you'll have to write down, well, what is my unknown number? And some people had a problem with the previous one. Essentially, the identification of your ID is in the file name. So you'll have, let's say, unknown X, unknown P, unknown W, whatever. That is your identification, all right? And once more, what I would recommend is that, like you did in the previous experiment, I hope you did, is that maybe you can come in here, right? And you can come in here and do like a flow chart. Remember, it's not the same flow chart that the lab manual gives you for a known mix. This would be for an unknown, and therefore you would have some boxes in there that are more like, add this thing. Do I get a precipitate or not? Yes or no. And depending on whether you get a precipitate or not at that step, you decide whether you go to the next one or not, okay? So I would put a flow chart here, and that would be kind of like a cool way of showing your evidence, showing your rationale for deciding, okay, what are the unknowns, the cations that I have present here in my particular sample, okay? That's the way the experiment works. And then what you'll do is you will come back to your assignment box in Canvas, and you'll make sure that you upload either pictures or scans, whatever file works for you. That's what you're going to upload into your assignment box, all right? Again, if you have any questions along the way, please do not hesitate to ask me, okay? Either contact me by email or in the Canvas inbox or by text. And again, please be patient with me. Realize that, I'm handling, this section plus 2 sections of Chem 1A. So sometimes I get a little behind and I'm not able to answer right away. I would recommend, please do not wait until the last hour of the due date to start working on this, because it's very likely that you're not going to be able to find me at 11 o'clock at night or whatever via Canvas, even though I'll probably be up, but I'm going to be checking my emails at that point. Okay, so thank you so much. I will download this video into your assignment box, and I will also download scans of the handwritten sheets that I had in here. Thank you so much, and I hope you have a great week.